Okay, everyone, we're going to get back to memory and dynamic arrays and stuff like that. We just talked about sizes of our different arrays or different variable types. And we're going to get to dynamic arrays right now. So, what we were looking at is pointers and variable declarations, and we even looked at static arrays. And I said, well, if you don't know the size of that array in advance, you sort of have to overdo it, right? You have to, I don't know how big this thing is going to be. I'm going to, make it twice as large as I think the maximum value is going to be, just to make sure I have the space. Planning that way in advance is kind of a bad thing. That's like hoarding when it comes to the pandemic, right? Where everybody bought way too much toilet paper. Why? But just in case. They didn't know if they're going to get toilet paper for 3 months from now or whatever the case was. So they bought 18 million, bags of toilet paper. Or some people were trying to resell it. That's a different thing. But a lot of people were hoarding food or hoarding toilet paper or whatever the case is. They didn't know what they would need. They overbought just to make sure that they had enough. That's what we would be doing with a static array. What we really want is, when I need it, I'm going to get it. When I need toilet paper, I go to the store. I know, very novel. Back in the good old days before the pandemic, you could go to the store safely and buy stuff. It's crazy. So we're going to, essentially, when I need something, I'm going to go to the store, get it, come back. That's it. That's the idea behind a dynamic array. So I don't know how big the array needs to be beforehand. So what at runtime, when I'm running my code, I'm going to say, hey, operating system, give me data. Give me a certain amount of memory that I can play with. All the other stuff, all our integers, all of our arrays, all of this stuff you could allocate it well beforehand. When you're compiling it, you could say, I'm going to need these resources. We don't have that option here with a dynamic array. It is, so a compile time, a static array, you say, I'm going to need an array with 400 elements. And it says, okay, we'll make sure when you run your program, we'll give you an array of 400 elements that you can use throughout the run of your program. Dynamic array says, I'm going to need something at some time. When I get there, I'm going to ask you for it. And the operating system says, okay, that's fine. And so you get to some line of your code and you say, I need an array of 4,000 elements. And it goes, oh, I got some over here, and passes it to you. That's a dynamic array. At runtime, not when I compile it, but when I try and run things, I will get that big chunk of memory. Now, as you might imagine, if I do not have that memory available to me, static arrays, if I didn't have that memory available, it doesn't allow me to compile it properly, or it won't let me run my program. Dynamic arrays, if I do not have that memory available to me, the program barfs on me. Essentially, the program gets, has an error in it, or something bad happens. In some cases, you can elegantly handle it. I don't get the pointer at all. I don't get the array at all, and I just sort of figure out what I need to do from there. But at the end of the day, once I've gotten my dynamic array and my static array act and are treated the exact same way. There is no real difference between the two. In fact, that is the little hidden secret of a static array. Everyone thinks it is this particular data structure, and it's not. It's just a contiguous chunk of memory that you're playing around in. And a dynamic array is the same thing. It's just a big chunk of memory that you're playing around in. It is, here is my memory with a whole, a big table full of memory, a whole bunch of contiguous rows, one after the other, and I'm just going to be able to stomp on parts of that memory. That's all it is. There's no magic involved. It is addresses in your memory on your computer that you are putting values in. They're both arrays. I have a starting address right here at the start of this array, whether it's static or dynamic. And in fact, that is what we're passing around with our arrays. So our array back here called mynums, the variable mynums is actually just shorthand for the address of the location for where mynums is located. Mynums is located right here, 00b23496. So the variable name mynums is actually just this address. That's all it is. Just the same way as My var as an integer is just the address. It's a shorthand. It's a name associated with the address where this data is located. Rather than having to remember a street address, it's like saying the name of the store versus the street address, right? The street address and the name of the store do match up, but sometimes it's a lot easier to say, oh, that particular building. Oh, you mean that building? Okay, that's I know where that is. So, by the way, also our static and dynamic arrays in C only allow the same type of data everywhere. I cannot have integers and shorts and this and that in my array. It is all the same type of array, the entire thing. We are going to need to learn about casting or review casting again. And more importantly, well, the important thing, the one last thing we need to know about dynamic arrays is when we're done with it, we need to give it back to the system. There is nothing in our program when we ask, live, is when we ask at runtime for memory, the system gives it to us, we say it's ours, and unless we give it back, it's still ours. It's like going to the library, getting a library book, and never giving it back. You can keep on taking library books out, right? And maybe at some point in time the library prevents you from getting more library books from them, but you can have a lot of library books before they start balking at you. Okay, so you get a bunch of library books, and then you never give them back. No one else is using those books. Those books are yours. If you lose them, if you misplace them, whatever the case is, nobody else is reading or accessing those books. They are yours. You have stolen from the library, and it's in your house, and no one else can use that. We can read those books. I like pointing that metaphor out because most of the time, when we get something from the library, we give it back after we're done, right? It is not, a static array is more like you go into the library and you read the book, right? It's not a matter, and if you left it on the table or you misplaced it, the library is going to find it again. When you take it out, when you actively take out a library book, you have to manually give it back at the end of the day. They're not going to come to your house to take it back. You have to bring it back. So in C, we get a number of bytes from the system. That's all we do with a dynamic array. We say, give me 80 bytes of data. And then we say, by the way, those 80 bytes of data, that's a bunch of integers. And when you're done, you say, and now I'm giving back those 80 bytes of data. That's essentially the process that we're going to do. So we ask for a chunk of memory, just memory, not integers, memory. We say, by the way, this is an array of integers. And then when we're finally done using it, we say, and here you go, here's your array of 80 bytes of memory back. Okay, this is what MALLOC is going to do for us. So MALLOC standing for memory allocation. It is not an Avengers villain. It sounds so like I am MALLOC the Destroyer. MALLOC is just standing for memory allocation. And what we pass in is how much stuff we need. That's item number 1. And when on top of that, it's just going to give you a void pointer. It is a pointer to something. That's what a void pointer is. Void, when we had void in other programs, we said void is when we don't return something. A void pointer it's a pointer to memory, but it's not really a variable of any kind. It's something or other. It's just a pointer, generic brand pointer. Okay, that's what a void pointer is. Each and every single time we call malloc, we do 2 things. We figure out how many bytes of memory we're going to need. And as a result, since it's the number of bytes requested, I need to figure out how big a character is and how many characters I'm going to be storing. That's where the size of comes in. It should be used each and every single time you call malloc. You should never ever hard code a number in there. Do not put the number 4. Do not put the number 1. Do not assume it's a certain size. You call size of. You should lose some points if you do not call size of. It's just a good habit to get into. So every time I say, I want an array of 20 characters, let's say, so the size of a character multiplied by 20, that's how many bytes of data I need. This happens to be 1 times 20, so 20, so I need 20 bytes, fine. And it's going to give me a pointer. What kind of pointer? Just a pointer to memory, generic memory. And I'm going to have to say, by the way, it's not just a pointer to generic memory, it's actually a pointer to a bunch of characters. This is a cast right here. I am going to say, this is not just any old memory. I am going to cast, it's going to be an array of characters. That's what we're doing. The cast allows me to say it is going to be characters and only characters. Now that I have that, I know I have a pointer to a bunch of characters. I have the very first position in that array for its characters, and I'm right back to where I was before. So in this particular case, a text right here, hopefully you can see my pointer, the pointer from the pen. A text is an array of 20 characters. It is going to be a character pointer, which is just pointing to the front of the array, and I can access individual elements in the array. The array is called a text. I can go to array element 1, 2, 5, whatever the case is. A cast, again, is no, it's not a void pointer. I'm saying it's a character pointer. Just the same way I can say, no, it's not an integer, it's actually a short, and just sort of forcibly change how the data is interpreted. That's what a cast is. I'm looking at data and say, no, it's not an unsigned int, it's actually an int. And now that really large value is now just a small negative value. That's what a cast is. It's forcing us to interpret it one way or the other. I want to make sure I use size of, because integers have actually changed in size. Longs have actually changed in size. The size of a particular student structure is, if I had the student structure from, I think, a couple lectures ago, if I did size of for a student structure, it was 128 bytes of data. I don't want to have to manually count that out. Just call size of. I can call size of on anything, on a pointer, on a struct, on whatever I want. So if it's an array of students, I call size of on the student structure, and I get how big a student is. Size of a pixel, I get how big a pixel is. In this case, it will be 20 bytes, but it is actually 20 characters, each character being 1 byte. Okay, so I cast every single time. This is one of the other memorization things we have in the course. Every single time I call malloc, what am I going to do? I'm going to cast it to the array type that I want. In this case, characters. I just put a star at the end. We'll discuss why there's a star here, but for the time being, the type of data you want to store, and then a star immediately afterwards. And I'm also going to say how big this is, and every single time I'm going to call size of. Whether I know how big that thing is or not, I'm calling size of. If you leave off, I know that a char is one byte in size. I'm going to leave it up. No, put it in. You're wrong if you do not put it in. It's just get into the habit of putting it in there each and every time, just in case. Okay, it also makes it a lot clearer what you're trying to do. So I'm making an array of characters, 20 characters. So I find out the size of each character, multiply by 20. That's how many bytes of information I need. And then I say, it's a character pointer. It's an array of characters, and not an array of just random memory. There are characters in particular. All right. And so we have 20 characters in total. So here would be me making the same. I'm going to call malloc and get 64 bytes of data each and every time for a whole bunch of different slides. So I could call malloc of 1 times 64. I don't want to actually ever type the word number 1. I should be using size of char. I wanted to show you what's going to happen when we go over a couple of these examples. A char is size 1, which is the same as me putting a 1. Size of char is the same as me putting the number 1 here, but I should always be using size of char. Just for this demo, I'm using the number 1 to really show what's happening. So each one of these is 1 byte, 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 all the way down. And I could just make I broke it down in a couple steps here. I made a void pointer of a demo. This is just a pointer to our generic random memory that we're going to be we got allocated from the operating system. Okay, the next step, I then cast that demo to being, it's an array of characters in particular. And then I'm going to use a for loop here just for craps and giggles here. I'm going to use a for loop and set every single one of the values in the array to the value 40. So 40, 40, 40, 40, 40, 40, 40, 40, 40. It works the same way as my arrays did before. All I'm doing is filling in every single one of these things in my array of 64 different characters. I'm putting the value 40. So I don't know what that is. That's the ASCII value, but it's some ASCII value. I think it's a non-visible ASCII value. Okay. I could put A if I wanted to. Okay, that is me allocating an array of characters. Here's me allocating an array of integers. Again, I should be using size of here, but I wanted to just show you I'm using size of an integer. I happen to know it. I put the 4 in there just to be very explicit what's going on. I should be using size of in a real example. So I will allocate 4 times 16, still 64. I wanted to break this down from our pattern we had before. So still 64, still 64. The math is the same, but I just broke it down into 4 times 16, still 64. And it's an array. This is making a demo is the exact same array between here and here. There is no difference between those two declarations. I could just put the same code in. It's an array of 64 bytes of data. That's what we're going to get here. And then I say, no, it's not an array of random data. It's an array of integers. That's what this thing here is. This is the cast. So a demo 3 is an array of integers. Notice what I have here. I actually have not remotely the same amount of stuff. In fact, I only have 16 slots. The same amount of data is being taken from the operating system, but I have 16 slots. In fact, this is what I actually have. In reality, I have a bunch of zeros in all the other character positions I had before. What my array looks like is if I converted it back to being characters, it would be 0, 0, 0, 20, 0, 0, 0, 20, 0, 0, 0, 20. But as an integer, 0, 0, 0, 20, all of those zeros in the front just means the number is still 20. It's 32. It's what size of it is 32. Yeah, okay. So I have 16 times, so it would be 4, yeah, and it's 4 bytes each. So I have 4 bytes or 32 bits for each one of these slots. Last time it was only 8 bits. So I have the number 20 using up 32 bits of information. The size of the bucket that I'm storing stuff in. This is essentially like a big bucket of data that I can store a number in. I'm only storing the number 20, but I still am using the full bucket here. The size of the bucket I'm using here is still 32. The size of the bucket I had before, the first buckets I had were 8. The bucket size is 8. The bucket size is 8. Nothing to do with the size of the number I'm putting in. This is a larger number than I had before, than I have here. But the size of my bucket, what I'm filling in, is 32. Before it was only 8. I could do this again, and so here's our each byte. I could do this again and use long longs. And so instead of, little characters each time, it would actually, each one of these rows, each row is actually one long. A long, so each long would be 8 bytes. So 8 times 8 is 64. Each byte is, so each long is actually 64 bits long for each one of these things. If I put the number 30 in there, it doesn't matter. I'm going to use up this entire 64 bits of information to store just the number 30. So I'll have a whole bunch of zeros at the front and then the value 30. You can actually see this if you actually run the code and put a breakpoint down. Again, I should be using the size of a long. This is actually the hard code. I could just hard code the value 8 in here. I shouldn't. I should use the size of operator. And I will make 64 bytes. I get 64 bytes of data, and I'll put that in. This is just me pointing to the start of 64 bytes of data. And when I go use my for loop, I'll only go over 8 spots because it's a bunch of long longs, and it looks like this. The data underneath the data I got from the system looks exactly the same. It is this many bytes, and how this gets allocated, how big the buckets are, how I sort of separate out my space depends on the kind of data I'm storing. That's the reason we do it this way. So, no matter what, malloc, I need the size, a number of bytes I'm going to be storing, and then I cast it to a particular kind, and that tells me how big each of these buckets are. All right. So I would like you guys to try this out. I would like you to make a dynamic array of 40 floats using malloc. Very important that you actually try some of this just to get a sense of it. We haven't locked at floats before, but you shouldn't need to. There shouldn't be any changes to things. So try this out and see how you do. I'll wait a little second or two, or pause the video and pick it up again in a second. Okay, so let's try this. I'm going to have a float. And what am I going to do? I'm going to have, it's going to be a cast. Always a cast. It's kind of float. These are an array of floats. And then I'm going to call malloc. I'm going to run out of space, which is nice. I ran out of space. That's the reason I went on another line. But this is all I would do. It's the size of a float multiplied by 40. That's how much space I need. And instead of just being generic random data, I'm saying, no, it's an array of floats. And now I can access individual elements in my array of floats. In fact, I can say something like a at position like 2, 3.7 F, and just put the let's make my F a bit better. That's the cursive version of F. There we go. And just put it at the third element, 0, 1, 2. I'm going to put 3.7. I can access individual things. And so let's put it as a comment. Use of it. Okay. So what I'm going to do next time around, we're going to be looking at pointers a bit more, and we're going to look at how we can deal with this whole bucketing and how we can free up our arrays and how we can look at our arrays again. So with that, take a little break. Make sure you understand what's going on with malloc. Try a couple examples, see how it goes, and then we'll pick it up. And then we're going to look at calloc as well. All right. Thanks, everyone.